welcome back. In this lecture, we are going to talk about discrete time modeling with closed current loop. So, we will first consider analog current mode control and their current loop stability with only inner current loop closed. Then we will talk about what is the stability criteria of the current loop stability criteria under mixed signal current mode control, and then we will see what is the stability criteria under fully digital current mode control, and then why do you need to go for closed loop stability analysis, that also we will see in this lecture, the motivation behind analysis of closed loop stability. So, first we will start with the current loop stability under analog current mode control. So, here you can see this is our peak current reference and we are considering the current reference to be constant. That means, here is my Iref and it is compared with the sense current, there is a comparator, and in current mode control there will be a latch circuit, and this is we are talking about the trailing edge modulation, that is under peak current mode control. So, it is under trailing edge PWM and peak current mode control. So, here we want to first write what is the equation. Okay, so, we want to write. So, this is under trailing edge modulation, this is under trailing edge PWM, and we want to write this In plus 1 in terms of In and want to check what is the stability of the current loop. So, first we will start with how can we write In plus 1 in terms of Iref. So, it will be Iref minus M2 into T of, the T of is this duration. Then we need to find how T of can be represented in terms of In. So, that means again we can write that Iref, another equation, that means In, which is this current, is equal to Iref minus M1 T on, right. So, these two are the two equations, and how do you relate these two equations? So, under fixed frequency modulation, that means if you are talking about the trailing edge PWM, then we generally write the on time, that means we keep on time to be duty ratio into time period. So, under trailing edge fixed frequency, we take the time period constant, and then we will replace T on equal to dt. Then what is T of? It is 1 minus d into T, and then let us substitute. So, first we will substitute in this equation and we will get this equation. Then the next equation again we substitute here, where T on equal to dt. Then we want to replace this intermediate variable dt in both the equation, and then we can get. So, dt will be from this equation, what is dt? It is Iref minus In by M1. Now, we want to replace this dt term in this equation and then want to find, and the detail of these derivations are discussed in our previous NPTEL course in lecture number 23. So, if you substitute, that means dt, that means what we got, dt is equal to Iref minus In by M1, and that we have substituted here, and then we will get the full expression. So, if you separate the term associated with In and if you separate the term associated with Iref and rest of the offset term, then what can we write? Now, this is the large signal current loop equation, where since we are keeping the Iref constant and we are not, that means we can assume under that small perturbation the slope perturbation is neglected. That means we are assuming that the perturbations of the slopes are neglected. So, that means under perturb condition this quantity will be 0 and we are taking M2, M1 are constant, and another condition we are initially considering a fixed current difference, that means the change in current, the perturbation in the Iref will be 0. So, if you set perturbation in the, that means another product perturbation we can ignore. So, there are two, so for this equation there are two terms will come out. That means one is that what is called 0 input stability, 0 input stability. What does it mean? So, under 0 input stability, the perturbation for the input is 0. So, here the control input is my reference current, because if the current loop is closed and the Iref is my control variable. So, I want to keep Iref to be constant, then we will consider Iref perturbation this tilde to be 0, but in perturbation initial condition is non-zero, that means we are only perturbing the initial condition. So, that is why it is called zero input stability. It is the stability only due to the perturbation in the initial condition, okay, and that is the sometimes it is also known as homogeneous solution, that will be unforced response. Another is that zero state stability. Zero state stability. Under this condition, we are not disturbing the initial current as if we are disturbing the reference, that means we are perturbing the reference current. So, how does it look like? Let us take a current waveform. Let us take, so just to give a visual understanding. So, this is my time domain and this is my inductor current. So, if we draw the nominal current, that means this is let us say this is my I ref and this is the nominal I ref and this is my nominal inductor current, like this. Now, the first case we are perturbing the initial condition, that means 0 input stability, this is case 1 and this is case 2. So, in case 1, if we consider the perturbation in the initial condition, that means let us say we are perturbing this. So, the current will reach here and then this perturb current will go, it will go and up to, since it is fixed frequency, it will continue. So, since we have applied a perturbation in delta IN as if, and we want to see the effect, the perturbation is delta IN plus 1, okay. So, it is going out of the screen. So, let us say this will be delta IN plus 1, that means the perturbation, effect of perturbation at the end of the cycle. So, this effect can be analyzed when we I ref perturbation is set to 0. So, this blue line corresponds to condition 1. The second condition, if we consider the second condition, so let us say green line, green. So, here we are perturbing this current, that means we are perturbing this I ref now. So, that means this will be my nominal I ref plus some I ref perturbation. Then how does this trajectory look like? So, under that condition we will consider, let us say this same, because we are not disturbing the initial current, but we are perturbing this current. So, it is coming like this. So, that means the effect due to this perturbation, that means this perturbation which is my delta IN plus 1 due to the change in delta I ref or tilde, I ref tilde is the perturbation due to the second condition. This is our condition 2. So, that means we want to see the first condition. If we keep the I ref constant and if we perturb the IN, then we want to see the natural response, whether the current loop is stable or not for a given constant reference. And the second case will be helpful for the closed loop stability analysis. And if you combine together, then the entire closed loop stability analysis can be carried out. So, and these things can be detail of this derivation can be obtained in lecture number 23. So, here if we want to say 0 input stability, that means we are taking only the inner loop current, inner current loop stability due to the perturbation in IN, that is the initial current, and that is why we are not perturbing the I ref. Then inner loop stability. So, this will be the perturb equation and it is a discrete time equation. So, we want this quantity, the whole quantity associated, that mod of this should be smaller than unity, and if you can ensure the mod, because it is a discrete time, that means that should be inside the magnitude, should be inside the unit circle. That means that location of this coefficient such that if we apply the Z transform, then you know what, if I apply Z transform, what will get? You will get IL tilde Z, and this will be Z for this n plus 1 plus m2 by m1, this whole thing 0. So, we have to ensure that Z, that means the Z equal to minus m2 by m1. So, we have to ensure that this minus m2 by m1, that should be always within the unit circle. So, it can be proved if we take the mod of this. And if we write m1 m2 expression for buck and boost converter, so we know that rising slope of the buck is v in minus v0 by L, for boost it is v in by L, for buck falling slope is v0 by L, I mean we are talking minus of m2 falling slope. So, m2 equal to v0 by L, and for boost it is v0 minus v in by L. Then if you substitute, then it turns out that if you simplify, that v0 by v in should be less than half, which means the duty ratio should be smaller than 0.5. So, only for closed inner loop, but we are not talking about the closed loop, it is just the inner loop closed. So, the requirement that duty ratio should be smaller than 0.5, but we will see in the subsequent lecture, even much lower than 50% duty ratio, you will end up with subharmonic oscillation when you close the outer loop. Okay. Similarly, for the boost converter, if you take again m2 by m1 and if you get v0 v in that term, because if you take mod of m2 m1, since both are positive, so it will be m2 by m1 should be smaller than 1, because it is always greater than 0. Then again it can be shown the duty ratio should be less than 0.5. So, it is an universal requirement, the duty ratio should be smaller than 0.5 with closed inner loop. Now, we want to say these things are already discussed here, but now we want to move forward, because I was giving some conceptual understanding of current loop. What will happen for mixed signal current mode control? Remember, in mixed signal current mode control, your reference current and the inductor current are in analog. So, one can expect for the same reference current, the mixed signal inner loop stability, that means the 0 input stability must be identical, and that because they are identical in terms of analog current loop. So, because only digital part will come here when the mixed signal will have a digital compensator followed by a D2A converter, that we have seen. After that, the IREF is in analog and all the current loop, comparator, latch circuit are in analog, which is identical to analog current mode control. So, with only closed inner loop for a fixed IREF, the stability must be identical, and if we again carry out the same process ILN plus 1, and if you substitute the dt from this expression, then this is the overall expression, and you can show in a subsequent perturbation that if you take the Z transform, it turns out again mod m2 by m1 should be smaller than 1, and since m2 by m1 m2 and m1 both are positive, so your requirement is that m2 by m1 must be greater than 0, which is true, and it must be less than unity, and again it will be less than 0.5. So, I am not going through all the steps, because we have already discussed for the analog current loop. So, the bottom line is this. So, the same as this, that means the 0 input stability are same, where IREF perturbation we are considering to be 0, that because it is analog current loop. So, we are only considering the initial perturbation, initial current perturbation, but I will show you that if we consider IREF perturbation with closed loop, then the stability criteria will be different even compared to your analog control and digital control, they will be significantly different because of the sampling effect. But in this case we are not showing that. Here in this case we are showing that the current loop only if we keep the fixed reference current, for fixed reference current, for fixed reference current IREF, the inner loop stability for both mixed signal and analog current mode control are same. Now, what will happen for fully digital current mode control? So, in fully digital current mode control, I think we have discussed in previous lecture. In that lecture, we have shown we want to take the sample of the current just before the switch turns on, because we are talking about trailing edge modulation, trailing edge PWM, right. So, we are just taking the sample before the switch turns on, but keeping in mind the conversion time as well as the computational time, we are actually using that sample current for the next cycle, and we are adding this RAM, which is this color. So, its slope is MC. So, that is the emulated RAM. That means we are getting the emulated current for nth cycle, that is equal to the inductor current of the n minus 1 cycle plus MC. That means because we want to emulate the current, right. So, I would say emulate current in the time domain. In the time domain will be MC2 into T, and this is during nth clock cycle. So, we are taking the initial value for the previous cycle, and the current cycle will use this RAM and update it. Now, the question is, one might think that if you under steady state, if you take the MC to be exactly identical to M1, that means if you take MC, the emulated slope, which is my emulated slope, and M1 is my actual slope, right. So, emulated slope and the actual slope. The actual, that means both are actual rising slope of the inductor current. So, this is, you can see, this is the actual blue color is the actual rising slope of the inductor current. So, one might think, if you want to get the exact current waveform inside the digital platform by emulation, so it is very much common that we want to take emulated current exactly equal to rising slope. First of all, that method is not robust, because what is M1? M1 is Vin minus V0 by L. So, in order to extract that information, you need to get input voltage information that you can sense, and you can pass through D2A convert ADC. Voltage you are already taking, no problem, but how do you get the inductor value? So, exact information of the inductance is not available, because inductance can vary. Even if you take the BH curve of the magnetic material of the inductor, it will show that as current increases, the inductor can decrease, because if you are pushing more towards the saturation region, then the inductance value decreases. So, as a result, this value may not remain constant, or there can be deviation plus minus 10-20% deviation. So, you may not know the exact value of L. Even if you try to extract the exact value, and if you want to set as the emulated, we want to see what is the effect. So, again, this is the basic equation of the current loop that we have derived, because if you take for the nth cycle, let us say this is my nth cycle. So, starting value is ILN, that is the initial value of this cycle. That means I will say this is the ILN, this value is our ILN. Then it will be, and this expression we have seen in the previous like a few slides back, that it is nothing but ILN plus 1 is ILN plus M1 dNt minus M2 1 minus dNt, where dNt is the duty ratio for this cycle. Okay. So, how do you get it? Let us say ILN, that is the value at here. So, if this is the value, this will be equal to, let us say, what is the final value? So, let us say it is the final value of this. So, IF minus M2 1 minus d of Nt, correct. Now, what is IF? IF equal to M1, sorry. So, IL equal to ILN, that is this value, plus M1 d of Nt. Now, you replace here, then you will get ILN plus 1 is equal to ILN plus M1 d of Nt plus a minus M2 1 minus d of Nt, and this is exactly this equation. Okay. So, next, okay. So, since it is overlapping, so I think I have already given the intermediate step to show how it is coming. So, now you can derive. So, next is that you can rearrange this equation, then what will do? Next, this dNt I have shown you, the dNt is, if it is now, if it is a fully digital, because we know dNt, it is now not straightforward, because dnt is the duty ratio expression. How are you getting the duty ratio expression? So the starting value of this cycle, it is coming from the emulated slope, and you can see this starting value for the emulated current, the starting value is the inductor sample value of the previous cycle here. So that's why it is IL n minus 1 minus I ref n, which is this cycle. This is the I ref n. I ref n minus IL n minus 1 divided by MC. MC is the slope of this emulated current. So since the emulated current start with IL n minus 1 and end at I ref n, so I ref n minus IL n minus 1 by MC is the dNt. Now you substitute this dNt here, okay? Then what will get? This is the complete equation. Now this term, let us say I take A equal to M1 plus M2 by MC, let us say. So say this is we have taken. So this is the one. Now I want to again do the perturbation, because I want to do perturbation and I want to see the effect. So here, if we perturb the initial condition, we can find out what are the requirement of the stability if the I ref n is constant. So now if we apply Z transform here, then since it is a part of term, there is initial condition is for this term. If we straight away apply the perturbation, it will be Z into IL Z, then IL Z, then this I have taken A. So this whole term I have taken equal to A, and then A into I ref Z minus this will be a Z inverse of IL Z. And then if you substitute, rearrange this equation, you will get IL Z by I ref Z equal to this. That means if you talk about only perturbation in the initial current, no perturbation here, then you will get IL Z this into Z square minus Z plus A, and that will be equal to 0 if I ref Z, this Z equal to 0, or basically there is no perturbation. So this is my 0 input stability. So 0 input stability, and this is the equation. If we perturb I ref, then how IL Z is also getting affected. So for 0 input stability, we have to ensure that the poles of this, that means the roots of this equation, if I say poles or eigenvalue whatever, so you can say root of Z must lie in the inside the unit circle, and that can be proved if you write this equation. So you are interested here, and that can be proved that it will be true if we take A less than 1. It can be easily proved, because if I write Z square minus Z plus A that equal to 0, I can write Z minus half whole square is equal to 1 by 2 square minus A. So I can write Z equal to 1 by 2 plus minus, if I take half common, what will get? Will get, so 1 minus 4A, correct? So now you can see A is always greater than 1. So from here you can say A is always greater than 0, 0, because all are positive, so it is common. Now if A equal to 0, then you can show that, suppose if A equal to 0, then Z will have two values, one will be 0, another will be 1. So that means one will be on the unit circle, another will be at 0 origin. But since A is greater than 0, so if you keep on increasing A, and when A become like a 1/4, then this term will be 0, so it will be half. That means if you draw the root locus, you will find the roots are slowly coming inside the unit circle, and they will be exactly identical when A equal to 1/4. Then again if you keep on increasing the value of A, again they will be different, and you will get, so for A greater than 1.4, so you will get complex conjugate. and if A become 1, then what will happen? Then you will get, that means A equal to 1 minus 4. So you can prove that the magnitude of Z will be inside the unit circle will imply that A must be greater than A must be less than 1. So that can be proved. I am not deriving. So that means if you take this, so this can be proved that A, that means A must be this, and this will be MC must be, that means what is A? It is M1 plus M2 by MC. So MC must be greater than 0, and for buck converter this is, that means your MC must be at least M1 plus M2, which means it is greater than rising slope. So you cannot set the emulated slope to be rising slope, it has to be greater, and but this is the minimum requirement only with closed inner loop. But once you close the outer loop, I am just showing an example because I will go to this closed loop analysis later. So here I am showing, if I just close the outer loop and if I set MC equal to 1.1 time, because this is greater than, that means I have taken MC to be greater than M1 plus M2. But with closed loop, you see the blue lines indicate there is subharmonic oscillation. This is for closed loop. So for that means the what condition you got, that is just for inner loop stability. But if you close the outer loop, because of the sampling effect and other effect, and that we will discuss, actual closed loop eigenvalues will go outside the unit circle and your current loop closed loop become unstable, and that is shown from the blue stage. But if you increase further, then you can make it stable. So it is interesting to show how this MC should be selected, and that will depends on the controller gain. But I am showing another approach of event sampling. You can get the detail in this paper, but it is not necessary. I am just showing that using this approach of digital current mode control, there is an alternative architecture where it is the emulated only, but the different sampling technique, and this is not covered in our lecture. This may be for advanced topic. But what I am saying, in the regular current mode control analysis for full digital, it will be unstable. Even just slightly increase higher value of M1 plus M2 is not sufficient. So you need to take even much higher with closed loop. So that means we need to go for closed loop stability analysis. So only inner loop stability is not enough, and we need a detailed system model. So in summary, we have discussed discrete time modeling with analog current loop. We have discussed the current loop stability under mixed signal current mode control. We have discussed current loop stability under fully digital current mode control, and all this we have only considered closed inner loop, not outer loop is still open. And we saw that with this only inner loop stability, we can ensure when there is no closed loop controller. But once we have the closed loop controller, then the stability requirement will further become complicated, and we need the full model of the system. So we will discuss this full modeling, the complete modeling of the switching converter in the next lecture. We will start how to do the complete model or discrete time model of the closed loop converter. So with this, I want to finish it here. Thank you very much.